Take the number 2 and multiply it by itself 5 times. You get 32. Now divide that by 5 and keep only the remainder, 2. You started at 2, you raised it to the 5th power, and the remainder brought you right back to 2. That is not a coincidence of small numbers. Take 3, raise it to the 7th power, and you get 2187. Divide by 7, and the remainder is 3. Again, the number came home. The pattern is this. Pick any whole number, raise it to a prime power, and divide by that same prime, and the remainder is always the number you started with. This is Fermat's little theorem, and it is one of the most useful facts in all of number theory. The strange part is not that it is true. The strange part is why the exponent has to be prime, and the cleanest explanation has nothing to do with algebra. It is about beads on a string, bent into a circle, and turned. Forget arithmetic for a moment and let us just count things. Imagine a short strip with 5 slots in a row, and 2 colors of bead to fill them, red and blue. How many different strips can you make? Each of the 5 slots is an independent choice between 2 colors, so the count is 2 times 2 times 2 times 2, which is 32. 32 strips, and every one of them is a genuine arrangement we can list. Now notice where those numbers came from. 5 was the length of the strip. 2 was the number of colors. So the count, 32, is exactly 2 raised to the 5th power. If we had used 3 colors instead and a strip of length 7, the count would be 3 to the 7th, which is that same 2187 from a minute ago. So the quantity a to the p, the very thing on the left of Fermat's theorem, is not mysterious at all. It is simply the number of colored strips of length p that you can build from a colors. We have turned a power into a pile of things we can count. That is the whole trick, and everything else is bookkeeping. Among those 32 strips, a few are special, and we want them out of the way first. 2 of the strips are a single solid color, all 5 beads red, or all 5 beads blue. Nothing else about them varies. Call those the plain strips, or if you like, the boring ones. With 2 colors, there are exactly 2 of them, 1 per color. With 3 colors, there would be 3, and in general, with the colors, there are exactly a plain strips, 1 solid block of each color. Set those 2 aside, and 30 remain. 30 strips that are not a single solid color. Every one of them uses at least 2 different colors somewhere along its length. In the general statement, we have taken the a to the p total strips and removed the a plain ones, leaving a to the p minus a of the interesting kind. Hold on to that number, a to the p minus a, because it is the left side of Fermat's theorem in disguise. If we can show that this pile of mixed strips can be sorted into equal groups, and count how many are in each group, we will have proved the whole thing. To sort them, we bend each strip into a circle, take one of the mixed strips, and join its 2 ends together, so the row of beads becomes a ring, a necklace. The instant it is a ring, something new is possible. We can turn it. Rotate the necklace by 1 bead, and every bead shifts 1 position around the circle. The bead that was at the top is now 1 place clockwise, and the bead that was at the end has come around to the front. It is the same necklace, the same beads in the same cyclic order, just spun. Do it again and again. With 5 beads, there are exactly 5 distinct turns you can make before everything returns to the start. Rotate by 0, by 1, by 2, by 3, or by 4 beads, and the 5th turn brings you home. Those 5 turns are not decoration. They are a mathematical action, a group of rotations acting on the necklace. And the question that cracks the whole proof open is simple. As you turn a necklace all the way around, how many genuinely different strips do you see? Let us actually turn one and watch. Start with red, blue, 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 blue. Turn it 1 bead. Now the strip reads blue, red, blue, blue, blue. Turn again. Blue, blue, red, blue, blue. The single red bead marches 1 step along the strip each time we rotate. After 5 turns, it has visited all 5 positions, and we are back to the start. So this one necklace, spun all the way around, produced exactly 5 different strips. That is the key move. Each necklace corresponds not to 1 strip, but to a small family of strips, the ones you get by rotating it. Mathematicians call such a family an orbit, and what we just saw is that this necklace's orbit has exactly 5 strips in it, the same as the number of beads. If that were true for every mixed necklace, the 30 mixed strips would fall into groups of 5, with nothing left over. 30 divided by 5 is 6, but we have to be sure the size is always 5. Why couldn't a necklace repeat sooner? Here is the heart of the whole argument, and it is worth going slowly. Suppose spinning a necklace brought it back to itself before a full turn, say after just 2 of the 5 clicks. Then the pattern of beads would have to repeat every 2 positions around the ring. But 2 does not divide 5 evenly. A pattern that repeats every 2 beads cannot close up neatly on a ring of 5, unless the repeating block is a single bead, meaning every bead is the same color. And that is a plain necklace, which we already set aside. The reason 2 failed is the reason everything works. The number of clicks it takes a necklace to return to itself must always divide the number of beads. That is a hard theorem about group actions, but on a ring you can almost see it. And when the number of beads is prime, its only divisors are 1 and itself. So the return time is either 1 click, which means the necklace never changed at all, and every bead is identical, or it is the full count of beads. Throw away the plain necklaces, and only the second option survives. Every mixed necklace on a prime number of beads has an orbit of exactly p strips, not fewer. This is the single place the whole proof spends its primality, and it spends all of it right here. Now we just collect what we have. The mixed strips number a to the p minus a. Every one of them belongs to some necklace, and every mixed necklace owns exactly p of them, its p rotations, all distinct. So the mixed strips are sorted into tidy groups of p, with none left over and none shared. A pile that splits perfectly into groups of p must be a multiple of p. In other words, p divides a to the p minus a exactly, and p divides a to the p minus a is precisely what it means to say that a to the p and a leave the same remainder when divided by p. That is Fermat's little theorem. Written out, a to the p is congruent to a, modulo p. We did not manipulate a single equation to get here. We counted one collection of colored strips and insisted that it be a whole number of necklaces. For our showcase that reads 30 mixed strips, 6 necklaces of 5, so 5 divides 30, and 2 to the 5th comes home to 2. The picture and the arithmetic are the same statement seen from 2 sides. A proof deserves a second look with fresh numbers. So let us run the whole machine again on a different case, quickly. Take 3 colors this time, and a strip of length 7. The number of strips is 3 to the 7th, 2187. 3 of those are plain, 1 solid block of each color, so we set aside 3 and keep 2184 mixed strips. 7 is prime, so the argument from before applies without a single change. Every mixed necklace of 7 beads returns to itself only after a full turn of 7 clicks, so every orbit holds exactly 7 strips. The 2184 mixed strips therefore split into groups of 7, and 2184 divided by 7 is 312, a whole number with nothing left over, exactly as promised. So 7 divides 2184, which says 3 to the 7th is congruent to 3 modulo 7. The remainder of 3 to the 7th divided by 7 really is 3, the same 3 we started with. 2 different starting numbers, 2 different primes, and the necklaces sorted themselves both times. Now for the question the whole video has been circling. Why prime? What actually goes wrong if the length is a composite number? Let us break it on purpose. Take a strip of length 4 and 2 colors, and look at the necklace red, blue, red, blue. Bend it into a ring, and turn it by just 2 beads. Red goes where red was, blue goes where blue was. It has come back to itself after only 2 clicks, not 4. Its orbit does not have 4 strips in it. It has 2. Red, blue, and blue, red, and that is all. That is the whole failure in one picture. 4 is not prime. It has a divisor, 2, sitting between 1 and itself. So a pattern can repeat with period 2 and close up on the ring, giving an orbit smaller than 4 without being plane. The strips no longer sort into equal groups of 4, and the counting argument collapses. And sure enough, the theorem itself fails here. 2 to the 4th is 16, and 16 divided by 4 leaves remainder 0, not 2. The number did not come home. Composite lengths let necklaces cheat, and that is exactly why Fermat needed a prime. There is a second, sleeker form of the theorem, and it drops out with one more step. Start from what we proved. A to the p is congruent to a, modulo p. Now suppose the base a is not itself a multiple of p, so a and p share no common factor. Then a can be cancelled from both sides of the congruence, and what remains is a to the power p minus 1, congruent to 1, modulo p. Raising such a number to the power 1 less than the prime always lands exactly on 1. Check it. 2 to the 4th is 16. Divide by 5, and the remainder is 1. 3 to the 6th is 729. Divide by 7, and the remainder is 1 again. Every base that avoids the prime, raised to 1 less than that prime, comes back to 1 on the nose. This version is the one people actually reach for, because a fixed answer of 1 is a sharp thing to test against. If you have a number and you want to know whether it might be prime, this gives you a lever. Raise a base to 1 less than that number, take the remainder, and see whether you land on 1. That lever is called the Fermat primality test, and it is genuinely useful, but it comes with a warning worth knowing. If you raise a base to 1 less than your number, divide, and the remainder is not 1, then the theorem has been violated, and your number cannot be prime. It has been caught. That direction is airtight. A failure is a certificate that the number is composite, no exceptions. The trouble is the other direction. Landing on 1 does not guarantee a prime. There are composite numbers that pass the test anyway, imposters that satisfy Fermat's congruence without being prime. The number 341 is the first. It equals 11 times 31, yet 2 raised to 340 is congruent to 1 modulo 341. To base 2, it looks prime. It is lying. Usually a second base exposes the fraud, but a rare and stubborn few, the Carmichael numbers, pass for every base that shares no factor with them. The smallest is 561. Those numbers are a story this channel has told before, so we will leave them at the door. The point here is only this. Fermat's theorem gives a fast, one-directional test, and the necklaces are the reason the honest direction is honest. Step back and look at what carried the whole argument. We never factored anything. We never manipulated an equation until the end, and even then only to read off what the count already said. The entire proof was a single insistence. A pile of colored strips must be a whole number of necklaces. Turning a necklace is a rotation. Rotations form a group, and on a prime number of beads, that group leaves every mixed necklace with an orbit of exactly the prime size. Divisibility was never assumed. It was forced by symmetry. Fermat stated this in a letter in 1640, and, as was his habit, left no proof behind. The first published proof came from Euler almost a century later, but the counting argument, the one with the beads, makes the strangest part ordinary. The exponent has to be prime because prime is exactly the condition that forbids a necklace from repeating early. The primality is not an accident of the algebra, it is the shape of the thing. A power became a count became a ring of beads, and a ring of beads, turned, proved a law that guards the whole of modern arithmetic. Not by calculating harder, but by looking at the same collection from two sides and refusing to let the numbers disagree.